Hello, today's lab is a short lab and it's on EKGs. So what we're going to talk about today is the electrocardiogram. And we learned about voltage and current in the past 2 weeks. So this is an application that uses voltage signals from your heart. So the objective, we want to observe and compare and understand different EKG, ECG waveforms generated in different settings. Now, this is going to be a simulation, and all you're going to do is look at the waveforms that are in the lab manual. So an electrocardiogram or an EKG, test is a simple, painless procedure for measuring electrical signals in your heart. So each time your heart beats, an electrical signal travels through the heart. An EKG test can show if your heart is beating at the normal rate and strength, or if it is not. And a doctor or a medical professional trained in reading EKGs can interpret the readings to determine if you need further treatment. So both muscle and nerve cells have an electric dipole layer across the cell. So if we look at this cell, the interior is negative and the exterior is positive, right? So here we have this dipole layer of a negative and a positive separated by some distance. And that is, in the normal situation, there is a net positive charge on the external surface and a net negative charge on the interior surface, as shown here. So here we have a muscle or a cell, the interior of the muscle or nerve cell, and the interior is negative and the exterior is positive. Just before the contraction of the heart muscles, changes occur within the cell walls so that the positive ions on the exterior of the cell can pass through the wall and neutralize those on the inside, and even make the inside surface slightly positive compared to the exterior. So as the muscle begins to contract, what we see is that the positive charges on the outside will neutralize the negative charges on the inside. And the interior will actually can become a little bit positive. So this is called depolarization. And the depolarization starts at one end of the cell and progresses towards the opposite end, right, as indicated by this arrow here. So what will happen is slowly these charges will move to the interior of the cell as the cell contracts or the muscle contracts. So the depolarization starts at one end of the cell and progresses towards the opposite end, as indicated by the arrows shown, until the whole muscle is depolarized. Then the muscle repolarizes back to its original state with the positive charges on the exterior and the negative charges on the interior. Figure C shows a rough graph of the potential as a function of time of 2 points, P and P prime, as the polarization moved through the cell. So we see is if we look at P and we see that the charge is 0 and 0 and 0 and 0, and then it goes slightly negative, and then it goes back to 0. And P prime, we see the voltage was 0, then it goes slightly positive, and then back to 0. So the path of depolarization within the heart as a whole is more complicated and produces the complex potential differences as a function of time. So each time the heart beats, changes in the electrical potential occur on its surface that can be detected using metal contacts called electrodes, which are attached to the skin. So the electrocardiogram is a graphic tracing which displays with a chart recorder on a paper or on a monitor of the potential changes for the given person's heart during the heartbeat. So the changes in potential are small. They're on the order of millivolts. So you were working with volts last week. So this is a thousand times smaller than that. So anyway, they must be amplified. So when they measure your heart, they put the electrodes on you, and then they have to amplify the signal because it's such a small amount of voltage. And this electrocardiogram provides information on the condition and performance of the heart. And electrocardiograms are made by applying electrodes to various parts of the body to lead off any tiny heart electrical potential and to the recording instrument. So here we see the anatomy of the heart, right? So we have the pulmonary valve and the pulmonary vein. We have the right atrium and the tricuspid valve and the right ventricle and the left ventricle and the left atrium and the aorta and the primary artery, pulmonary artery, excuse me, right? So this is roughly what the heart looks like. So if we look at the electrocardiogram, it looks something like this. It's just a measure of voltage versus time, okay? And the normal electrocardiogram shows typical upward and downward deflections and reflect the alternate contractions of the atria and of the ventricles of the heart. So it's standard procedure to divide a typical EKG into regions corresponding to the various deflections or waves shown in the figure. So the first deflection, P, which is shown here, is due to the atrial contraction and is known as the atrial complex. The other deflections, Q, which is a negative deflection, R, which is another positive, S, which is negative, and T are all due to the contractions and are known as ventricle complexes. So the first upward deflection, P, is due to the atrial contraction and is known as the atrial complex. Identification of the normal QRS complex from the P and T waves. So note that these kind of look like waves here, and here these kind of look like pulses, right? So the identification of the normal QRS complexes from the P and T waves does not create difficulties because it has a characteristic waveform and a dominating amplitude. This normal amplitude is about 1 millivolt. So from the ground, right from here to the top is about 1 millivolt. And the normal duration of QRS is about 0.08 to 0.09 seconds. The P wave has an amplitude of about 1/10 of that, so it's about 0.1 millivolts, and a duration of about 0.1 seconds. And the T wave, both of these numbers, for the T wave, both of these numbers are about double. So the T wave has an amplitude of about 0.2 milliamps and about 0.2 seconds is the duration. So the T wave can be differentiated from the P wave by observing that the T wave follows the QRS complex after about 0.2 seconds. So We watch this QRS complex, and then about 0.2 seconds later, we get the P wave. So if we want heart rate, right, we'll look at the beats per second, and it's just the number of R waves divided by the seconds that you count. So we'll have a whole bunch of these run by. We'll count the number of these R waves and divide by the time, the interval that we timed. If we divide by 60 seconds, we can convert it to beats per minute. So the heart rate, beats per minute, is the number of R waves divided by the time interval divided by 67 seconds. So if we want, we can count the number of R waves in T seconds and multiply by 6. Right, so we end up with is the number of R waves, the time that we measured, divided by 10 times 6. Finally, we can measure the R to R wave interval and then divide by 60 by the R to R wave interval, right? So what we end up with is 60, and the time divided by the time for the R to R wave interval. So for instance, here's an electrocardiogram. And if we look at this line here, it's at 0.25. Okay, and here it's at 0.075, right? And if we take this and divide it by 2, we get 0.5. So between 0.25 and 0.5, there's 1, 2, 3, 4, 5 divisions. So each of these subdivisions, right, is 0.05 seconds. So for instance, if I look at these two P waves, these two R waves, we end up with about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the time between these two peaks is 12 times 0.05. And that's how we would get the time. So in this example, the R to R interval is obtained as follows. First, we count the number of subdivisions, 12. And we have 12 times 0.05 seconds for each subdivision is 0.6 seconds. And then the heart rate, or the beats per minute, is 60 divided by this time interval. So we get 60 divided by 0.6 equals 100. So what you're going to do is look at figures 4.7 and 4.8 to complete the lab procedure. You don't have to do any drawing. There's no spreadsheets required. And you can submit your lab report and answers using the link EKG in the EKG lab folder. So this will be due a week from today, which is Wednesday. And once again, if you go to your Blackboard page, and we'll look for EKG, and the manual is here. So go ahead and read the lab, and then we'll use 4.7 and 4.8 as data for your lab. So there's a couple of questions for you to answer. And right now it's hidden, so let's make it available, okay? And you can submit your lab report by just answering these questions. So for example, it says, estimate the heart rate, count the number of R waves in 10 seconds, and multiply it by 6. This is the results per minute. Once again, to do this, we'll use the two diagrams in the lab manual. All right, thanks a lot, and I will talk to you later.